Hello viewers, very good evening to all my viewers. I again welcome you all back to this YouTube channel. We were discussing the past few lectures. We started with that, that intake, this facilities, design of intake facilities, or you can say not all, the design also, some numerical problems also we will solve here. See that here the drawings are already diagrams which were drawn in my earlier this class also. I have to erase here. I think you have understood this, because on this actually we have already discussed the various aspects of this intake facilities for a public water supply system using surface water source also. That already we have discussed. Now I am erasing this one, right? So we will continue the intake facilities here, solving some very common numerical problems also associated with the intake facilities and its component also. Various components are there, as we have already discussed, that the suction well, then intake, the port, then intake gate, then screens or racks or so. These already we have discussed. We also have given that the design, parameters and the design criteria based on standard references by CPHEEO Manual. Already I have told, I don't want to repeat this one here. This actually, and the other as usual, the American Water Works Association and the other references also, as already discussed. Now today we will have, first is that we already have discussed suction, this pipe also, for the well also. The suction pipe we have discussed while we were discussing the intake facilities also. That means here that the through suction pipe actually, because that pumping, which I already have told that the details of pumping or the water conveyance facilities we will discuss in the next this class after completing this intake facilities also. And the pumping, this one associated with this, that raw water pumping also after this intake also. There you will see that either this way or providing a separate pumping station also, that could be sort of designed separately, or in the intake well itself there is a suction pipe also, and the pump actually delivers the water through delivery pipe also. That is the pumping, and I will sort of advise all of you that, so that you know that pumping system, because the civil engineers actually many a time we have seen they lack actually that the knowledge of pumping and how the basic that the pumping system, how it works, and what are the basic parameters of pumping, and how to sort of find out the capacity of pumping, setting aside the other this mechanical details which actually do not belong to the civil engineering discipline also, but mechanical people, they do the pumping, this the design of the pumping impeller and all these things. But we will take from the market, say from the manufacturers or suppliers or so, we will use the pump this one here, for the intake facilities. in consultation with the manufacturer or suppliers, and then we will provide, and for every pump in fact, right, every pump in centrifugal type or submerged this pumping also, the suction pipe, one is suction pipe. Suppose this is the pump, right, this is the pump. There is a suction pipe through which that the water is water is sucked or pulled up, and there is a delivery pipe, right, there suppose there is a delivery pipe. So delivery pipe, through that actually the pumping is ultimately sending or transmitting the water to the desired end also, right. And where it will be, that details I will discuss later. That means what would be the head, what would be the discharge, and all these, the pump capacity also, and the requirement of pumps, that I will discuss later. But here the example we will start with that design of, example say 1, design the suction pipe and backwashing pipe for a flow of 3.79 meter cube per minute. Okay, now solution is very simple, So I am starting with the basic, solution to the basic problems also, numerical problems associated with this pumping for the intake, these facilities, or as a part of, or as a component of the pumping or intake well also, intake works also, right. So this is, assume the velocity of water through the suction pipe. So the velocity we are assuming that as per the design guidelines also. I have discussed already this one, you can just refer back our this discussion, previous discussion, the earlier discussion also. So velocity we are assuming, that 1.5 meter per second. That is, say, assume as per standard design guidelines, which already I have discussed. So the cross-sectional area of the pipe of the suction pipe so pipe, suppose this is the pipe, so if you see this one, so this will be looking like this, right. If you see the chalk, if you cut, suppose this is pipe, hollow inside, so if you cut this one here vertically, so you will get the round. So this is the cross-sectional this shape, and the area when we will calculate simply by dividing this flow meter cube per minute divided by velocity 1.560 meter per second, right. So if we multiply by 60, directly I am doing, so this would be meter per minute, remember this. So we are converting this by multiplying by 60, because 60 seconds make 1 minute or so. So we will get that per minute also, because as it is expressed in minutes, so we will convert for maintaining the consistency of the unit system also. So this is coming, you can check the calculation. I have checked this, right. So the diameter I'm taking, because I have rounded up this one here, right. So this would be 0.23, okay, yes, same thing, I have in fact rounded off this diameter. So this would be this much meter square, and you know that pi d square, d is the pipe diameter, inside diameter, this is always inside diameter, okay. So this is 0.042 meter square, from which you will get diameter is equal to 0.23 meter. that is pi d square by 4, so you can get the d, that is 0.23. I think all of you understand this. And when you calculate these things in case of 5 or so, then you see that, I mean, when you are providing that pipe or so, then you cannot take exactly that 0.23 meter or so. It has to be, you know, I mean, the higher side, right, which is available nearest this higher. So that will be available in the market. So commercially available the pipe sizes you have to, I mean, go through, and you have to talk to the manufacturers or the suppliers also, and then next higher size you have to take which will be available from the manufacturer or supplier also. So that way we actually have selected, right? So say 0.25, this is available in the market, or 250 millimeter. Okay. Now quantity of backwashing, quantity of water for backwashing, and this I have already mentioned in my last or before last, or so I don't remember, that this quality of water should be, I mean, very clean, in the sense that it should not contain that, you know, the debris and other things also, because ultimately it is going to the treatment plant. So that I mean, the water standards, quality standards are to be maintained. So that is why clean water it should be, you know, I mean, used for this. For backwashing, I am writing in short. Backwashing already we have written here. So this will be in fact 1/3 of Q. Q means this design Q. If we say that this is Q design, so we will write Q design. So this would be, say, 1/3 into 3.79 meter cube per minute or so. So this will be 1.267 or so. 264. Sorry, this is meter cube per minute. You can calculate this. I have already checked that, but still I will suggest you to calculate once more at your level. So the cross-sectional area, this is the cross-sectional area, many a time we write like that. Cross-sectional area of pipe, the backwash pipe of course, this would be 1.264 meter cube per minute. Why I am writing all this one? Because many a time we have seen that the students or even the engineers, you know, the beginners, so they actually don't mention the unit, but that is actually that should not be, right? You always mention the unit, numerator, denominator also, so that this will be consistent and your unit consistency will be correct also. So this into 3.05, we are assuming the velocity of water in the backwashing pipe, right? This is the assumption as per the design guideline, remember. Okay, so backwashing velocity, this actually we should have written that assuming a backwashing velocity of 3.05, which is recommended by many literature also. So that is why we have taken 3.05, you know, that into 60. 3.05, roughly you can say that 10 feet per second also. So this is this into 60, so this will make meter per minute, because this actually at 3.05 meter per second assumed. Okay, so that actually will give that this one I am writing here 0.267 0.007 meter square. Okay, you can check this. So 1.6, I don't know, I don't remember whether I have checked this or not. 1.264 divided by 3.05 into 60. Yes, actually this is 0.0069, so we have taken 0.007. So we are writing, say, approximately this one. And the diameter, same principle, using the same formula also. This actually will give or will require a diameter of pi d square 4 again. So this is the d for, right, this is this d, well this d, maybe the suction pipe you can write, backwashing d bw, say, that time the s you can write, suction. So this will be 0.094 meter, say, to round it off and to select the next higher size also. So this will be 100 millimeter, that means 0.1 meter or so. So 100 this millimeter size we have provided here. So that is the very simple, you know, that problems I have taken, so that you can, initially don't get stumbled also with this, you know, very complex kind of numerical problems or design problems also. This is very simple, right? So I'm not repeating this one here. So example 2, we will switch over to example 2, right? So this actually, for the same, this one, flow, design a strainer for a flow of this. Design a strainer. Strainer, we have already used strainer. We have already discussed this one, rather. That is in our, past lectures or so. But maybe the last time also we have discussed this strainer. So the strainer, the figure is there. You see that remains in on the board. So design a strainer for a flow of same thing. I'm just here, right? For a flow, continuation. Design a strainer for a flow of this. Okay, so assume, because suction pipe you have used, so for that actually you have to design the strainer also, because the suction pipe to that actually the strainer is at the mouth of the suction pipe, or the at the tip or so, that means at the beginning. So that actually is fitted to the pipe also, right, the strainer. So assume the velocity through the strainer at on net area basis, because the velocity, whenever it is mentioned, you know, that is actually, that is to be clarified, because I have tried to clarify earlier when we were discussing the design guidelines also, that whenever you take a velocity or assume a velocity or mention a velocity also, it should be written, it should be made clear that whether it is on the gross area basis or the net area basis also. Here it is net area basis 0.15 meter per second or so. So the effective open area, effective, or you can say the open area, that will be 3.79. This is just a matter of calculation only, right? So 0.15 we have assumed again multiplying by 60 to make it meter per minute. So this will be 0.42 meter square. Say this is equal to A, right? So the gross, as per the guidelines, right? So that actually gross area is more or less 2 times this net area, 2A. Okay, so this will be 2 into 0.42. Gross area means this opening as well as solid area, right? So both considering that is the gross area. Open or effective area means that only the perforations which are actually made on this strainer also. So that will be the effective, this open area or effective area also. This would be meter square. So this would be 0.84 meter square, right? Now 2 options are there, as I have discussed earlier also, that either the bell mouth like that, it is a mushroom type, right? So this is pipe is this suppose this way pipe is going, so this is this dome, right? So that is I don't have it, otherwise I could have shown this one, right? So that is the dome type, this one. I think you can sort of do that. So that actually you see that just 1 minute please. So the mushroom you must have seen, right? So that actually is a shape, one kind of shape is that. So this is the bell mouth type. So this is the first option is the for the bell mouth strainer. It is a bell like this one, right? So that is why it is like. So this is actually area, so from which the diameter you can get pi d square by 4 again, right? So that would be, say, diameter is calculated as 1.034 meter or so, right? So that is the diameter. By applying by pi d square by 4 and equating that area is equal to 0.84, we have calculated this. So this is you can provide either the 1000 millimeters, that is 1 meter or so, right? So that you can use as a little lower size, and higher size also you can go for. Say next size is available, from the market supplier, that next higher size you can get. So it depends on you, and in that case actually if you select lower size, remember always you have to check back the velocity and whether it is in the recommended range or not, right? So that is very important, that when you will sort of design or solve the numerical problems also, you should when choosing this one or selecting a pipe size or so, then the higher size obviously will give you the lower velocity, okay? And lower size if you select, next lower size say 1000 we have selected here, so in that case actually it will be, the velocity will be little higher also. So accordingly you have to sort of check the recommended range also. So provide this. So say we have chosen 1000 millimeter because this is readily available in the market. For the cylindrical, that also I have discussed earlier, cylindrical part. Here I think the drawing was there, you can just refer back our earlier discussions. So this is the cylindrical type of strainers. So that actually of height 0.61 meter and without any holes on the top, right? And providing a height of this without any holes, right? Without any holes on top. That means it is something like that. Cylindrical means this. This is the cylindrical type. So holes are there, but not on the top, because it is all solid. There is no hollow kind of this one, right? So this actually, the hole is not there. So entire this one, the water collect this water, it is fitted with the pipe also, right? Suction pipe, and the water comes when the suction through pumping in the further downstream, the water comes through that, right, from the intake, inside the intake well also. So that actually comes like that, but without any holes. It may be containing holes on the top, as I have already discussed this. I am not going to repeat this discussion. So cylindrical type, that is this, and then the perimeter and diameter. The perimeter is, that is P say of that, because the perimeter actually you have to see, because your velocity will be according to the perimeter available, because this is suppose the chocks. So this is suppose cylindrical, this one. Just consider this as a cylindrical strainer having perforations all around throughout the height, right? But on the top there is no perforation. So it is actually sucking water from this actually. The top also may be perforated, and to that pipe is fitted like that. Okay. So when this is coming like that, perimeter is important, because this through perimeter actually, that calculations has to be done, that what will be that, and in the market also you will have to state about that what is the perimeter you require for that. So cylinder perimeter P is equal to say 0.84 or so by 0.61 so. So that is actually 0.89 by point. But in the reference actually where from I have taken, that is they have taken 0.89, right? 0.89, because that is the area available in the market. When you will state, you better state not perimeter exactly, but the area you state. So area, say this area what you get 0.89 or so, where I have written this one. Yes, so this is gross area is 0.84. So for cylindrical one, we have suppose taken this area little higher, say 0.89, because this is the size market, this one, this is available. So this is 1.312 meter. I may explain this one, and you can see that on internet also it is available, that cylindrical this one, area wise, you have to say that area and diameter also. So perimeter is this, the perimeter we have got this way, that is this much meter or so, and the diameter, because ultimately you have to calculate the diameter. So pi d is equal to, right, diameter, perimeter, as you know. So this is the perimeter, so this is equal to pi d. So your diameter will be this by pi, right? So this would be your 1.312 divided by pi, or 3.14 or so, that would be 0.42 meter, or say 450 mm diameter cylinder with a height 0.61, and you know that the top does not contain any holes, only side, this one, right? So these are the very various numerical problems. For today I will stop here. So tomorrow or so, next lecture, we will continue that design. Okay, thank you so much. This is a very simple this one. We will gradually enter into a sort of, real intake, and its design also a very simple design will take, because the design of intake, if it is done in an elaborated way or so, elaborate design will take much time. So that is outside the scope of this particular online course. So that is why if anybody is personally interested, he or she could contact us, and we will definitely take a one-to-one interaction lecture or so, and that will be obviously paid, as we have already stated that for every this one, I think this one is written, but the subscriber also, the registered subscriber, they can get the information from us. That means what will be the package, right? That say individual, group package, then one-to-one interaction. So what will be that one? I will rather better give next time, if I could remember that one. I have to remember, because that you should know that what will be the subscription package also for different, size of the audience or viewers also, right from individual to the group containing say 25 members, 50 or 100 like that, and one-to-one half an hour say discussion on Google Meet or so that we will discuss later. Thank you so much. Okay.